Today we'll be discussing high availability in cloud systems design. Subscribe to the channel and like this video for more great cloud tips. High availability belongs to the reliability side of cloud systems design. It is the practice of minimizing downtime by spreading a workload across independent failure domains. Those domains are usually availability zones. Sometimes they are entire regions. An availability zone is a separate data center with its own power, cooling, and network. Spreading across zones means the loss of one building removes capacity. It does not remove the service. The word high is doing real work here. No design reaches 100%. You are choosing how much downtime per year you are willing to pay to avoid. Availability decides how far your architecture has to spread before you write a line of code. A simple application aiming at 99.9% uptime can often run in two zones behind a load balancer. A mission-critical system aiming higher has to survive a whole region going dark. That changes your data layer completely. That target is the difference between one database and a replicated one, and between one pipeline and several. Why decide this early? Getting it right early is cheap because zone spread is mostly a configuration decision at launch. Retrofitting it later means migrating data and rewriting session handling. It also means retesting every failover path you never had. Learn more at systemsarchitect.io. Like and subscribe to the channel and playlist. A single point of failure is any component whose loss stops the entire system. Finding them is the core exercise of availability design. It is more mechanical than it sounds. Trace one request from the client to the database. At every hop, ask what happens if that box disappears. One web server, one NAT gateway, one database instance, and one certificate all fail that test. The fix is redundancy, meaning more than one of anything on that path. Place those copies in different zones. Redundancy only counts when the copies are genuinely independent. Two instances in the same zone still share a power failure. Redundancy is useless unless traffic stops reaching the broken copy. That job belongs to a load balancer paired with health checks. An application load balancer distributes HTTP requests across targets in multiple zones. It probes each one on a short interval. After a few consecutive failed probes, the target is marked unhealthy. It is pulled from rotation within seconds. Autoscaling closes the loop, terminating the failed instance and launching a fresh one from the same template. Design your health check to test the path that matters. A check that only confirms the process is listening will happily pass while the application is broken. There are two shapes for redundant capacity, and choosing between them is a cost decision. Active-active means every copy serves live traffic all the time. Failure of one copy just removes its share of capacity. Recovery is close to instant, and you are always testing the standby. Active-passive keeps a second copy warm but idle until failover promotes it. That is cheaper and simpler, but the failover step takes time. It is only as good as the last time you rehearsed it. Amazon RDS Multi-AZ is the classic active-passive pattern. It promotes a standby in another zone in a minute or two. Most real systems mix the two, running stateless compute active-active and databases active-passive. Spreading compute is easy, and spreading data is where availability gets expensive. Synchronous replication writes to both copies before acknowledging the client. The standby loses nothing on failover. The cost is latency on every single write. That is why it is practical across zones and painful across regions. Asynchronous replication acknowledges immediately and ships changes in the background. It adds almost no write latency. The cost is replication lag. A failover can lose the last few seconds of writes. What about read replicas? Read replicas improve read availability by serving queries from copies, but a lagging replica can hand a user stale data they just changed. Aurora blurs the line by replicating storage 6 ways across 3 availability zones. Availability is quoted as a percentage of uptime, and the shorthand is counting the nines. 3 nines, or 99.9%, allows about 8 hours and 45 minutes of downtime a year. Four nines, or 99.99%, allows roughly 52 minutes a year. And five nines, or 99.999%, allows about 5 minutes a year. Each additional 9 typically costs several times the last one. The number should come from the business, not from ambition. Recovery time objective is how long you may be down. Recovery point objective is how much recent data you may lose. Publish those as a service level objective. Remember that a provider's service level agreement covers their service, not your architecture on top of it. Multiple zones protect you from losing a building, and only multiple regions protect you from losing a region. Cross-region designs use Route 53 health checks with failover or latency routing. That moves users to a healthy region. Data follows asynchronously through S3 cross-region replication, DynamoDB global tables, or an Aurora global database. This is a real step up in difficulty. You inherit conflict resolution, higher cost, and data residency questions. The principle that keeps multi-region failover honest is static stability. A statically stable system survives a failure without needing to make new control plane calls. Control planes are exactly what struggles during a large event. In practice, that means pre-provisioning the standby capacity you will need. Do not trust that you can launch it mid-incident. The best available systems degrade rather than stop. Graceful degradation means shedding non-essential features so the core transaction keeps working. A store whose recommendation service is down should still list products and take payment. It just does it without the suggestions. A circuit breaker makes that practical. It cuts off calls to a dependency once its error rate crosses a threshold. The bulkhead pattern isolates the damage further, giving each dependency its own connection pool. Add aggressive timeouts and retries with exponential backoff. Retries without backoff turn a small blip into an attack on your own backend. None of this counts until you have watched it work. That is what chaos engineering is for. A WS fault injection service can terminate instances or simulate the loss of an availability zone. You run it on a schedule you control. The direct benefit is revenue protection, since downtime in a transactional system is orders you never get back. Operations improve just as much. Failures that used to be incidents become events you read about the next morning. The same zone spread that survives a failure also survives a rolling deployment. You ship more confidently and more often. Availability is increasingly a sales requirement too. Enterprise customers ask for your uptime commitment before they sign. There is a security angle as well. Redundant capacity absorbs traffic floods that would flatten a single instance. Every 9 costs meaningfully more than the last, so match the target to what failure actually costs. An internal tool, a prototype, or a batch job that reruns tomorrow does not justify multi-region anything. A single zone deployment with tested backups is the honest answer. Complexity is itself an availability risk. An elaborate failover mechanism usually fails during the very incident it was built for. Availability also does not replace backups. Replication faithfully copies a dropped table to every standby you own. When the requirement is genuinely extreme, ask whether the whole system needs it, or only the small critical path inside it. High availability is minimizing downtime by running redundant capacity across independent zones or regions with automatic failover between them. It matters modestly for a simple application chasing 99.9%. It becomes the defining constraint for mission-critical systems. Build it by eliminating single points of failure, choosing your replication and failover model deliberately, and testing the failure before your users do. Thanks for checking this out. Hope you learned something. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io.